In 1965, two Bell Labs engineers pointed a horn-shaped antenna at the sky and detected something that shouldn't exist. Arno Penzias and Robert Wilson expected silence from empty space. Instead, they found a persistent hiss of microwave radiation coming from every direction at once. The signal measured approximately 2.7 degrees above absolute zero. What they discovered was the missing piece of one of astronomy's oldest puzzles. For over 2 centuries, scientists had wrestled with a simple question that threatened to shatter our understanding of the cosmos itself. If stars stretch infinitely in all directions through space, why doesn't the night sky blaze as bright as the sun? This deceptively simple question, known as Olber's paradox, exposes a fundamental contradiction between what we observe and what basic geometry predicts. In an infinite universe packed with stars, every line of sight from Earth should eventually terminate at a stellar surface. The night sky should appear uniformly brilliant, turning midnight into blazing noon. Yet darkness surrounds us, creating a paradox that would ultimately reveal the universe's deepest secrets about time, space, and the nature of light itself. The darkness problem first surfaced in 1576, when English astronomer Thomas Digges questioned why infinite stars would leave dark patches in the sky. Johannes Kepler tackled the puzzle in 1610, proposing the universe must be finite in size to explain the observed darkness. But the mathematical contradiction wasn't formalized until 1743, when Swiss astronomer Jean-Philippe Loyd de Chazeau calculated the precise problem 80 years before Heinrich Olbers made it famous. Chazeau divided the universe into spherical shells, each 1 light-year thick, extending outward from Earth. The second shell contains 4 times as many stars as the first shell because volume increases with the cube of distance, but each star in the second shell appears 1/4 as bright due to the inverse square law of light. 4 times the stars at 1/4 brightness equals exactly the same total light from each shell, regardless of distance. With infinite shells contributing equal light, the total should be infinite, heating the universe to stellar temperatures within 10 to the 23rd power years. Edgar Allan Poe, the American writer, proposed a startling solution in 1848 that anticipated modern cosmology by decades. In his philosophical essay Eureka, Poe reasoned that light travels at finite speed everywhere in the universe, and most importantly, there must be a time in the distant past before any stars were shining. His conclusion captured the essence of the eventual resolution. There simply has not been enough time for light from distant stars to reach us. Poe lacked mathematical tools to prove his insight, but his logical reasoning was remarkably sound. Dust absorption seemed like an obvious solution, but this explanation fails upon closer inspection. When dust absorbs starlight, that energy must go somewhere according to thermodynamic principles. Absorbed energy heats the dust, which then radiates as a black body at its temperature. If dust absorbed infinite energy from infinite distant starlight, it too would heat to stellar temperatures and glow. The night sky would appear bright in infrared rather than visible light, merely shifting the problem to different wavelengths. The finite number of stars also provides insufficient resolution. The observable universe contains approximately 10 to the 24th power stars within our cosmic horizon. Even with this vast but finite count, the fundamental question remains, why isn't there significantly more light than we actually observe? Recent Hubble observations revealed the universe contains roughly 10 times more galaxies than previously estimated, making the darkness even more puzzling if the universe were static and eternal. The primary resolution comes from a measurement that changed everything: the universe's finite age. The Planck satellite's final data from 2018 revealed the cosmos began 13.796 billion years ago, give or take 12 million years. This finite age creates what cosmologists call a particle horizon, a boundary beyond which light has not had sufficient time to reach Earth since the Big Bang. Light travels at 299,792 kilometers per second, but even at this incredible speed, photons from sufficiently distant regions simply haven't completed their journey to us yet. The observable universe extends to roughly 46 billion light-years in radius, larger than 13.8 billion light-years because space itself expanded while the light traveled toward us. Only this finite volume can contribute light to our night sky, and finite volume means finite total brightness, regardless of how many stars it contains. The universe has existed for merely 10 to the 10th power years, but reaching thermal equilibrium at stellar temperatures would require 10 to the 23rd power years. Our cosmos remains in its youth, having accumulated only a tiny fraction of the thermal energy needed to create the blazing sky that Olber's paradox predicted. The second component of the resolution involves a phenomenon that Penzias and Wilson unknowingly detected: cosmological redshift of ancient light. When electromagnetic radiation travels through expanding space, the wavelengths stretch in proportion to the expansion itself. This differs from Doppler shift caused by moving sources. Cosmological redshift results from the metric of space-time changing with time as the universe grows larger. 378,000 years after the Big Bang, the universe cooled to 3,000 degrees Kelvin, triggering a cosmic transformation called recombination. Before this moment, the early universe existed as hot plasma where free electrons and protons scattered photons continuously, making space completely opaque to light. When temperatures dropped sufficiently, electrons and protons combined into neutral hydrogen atoms, suddenly making the universe transparent for the first time. The photons trapped in the plasma broke free and began traveling through space unimpeded. These same photons surround us today as the cosmic microwave background, but 13.8 billion years of cosmic expansion has stretched their wavelengths dramatically. The expansion factor since recombination reaches approximately 1100 to 1, shifting bright visible light at 3,000 degrees down to microwave radiation at 2.725 degrees Kelvin. If human eyes could perceive microwaves, the night sky would indeed appear uniformly bright in all directions, exactly as Olber's paradox predicted. The COBE satellite's instruments measured this background temperature, 2.728 degrees plus or minus 0.004 degrees Kelvin. The cosmic microwave background represents the most perfect blackbody spectrum ever observed in nature, confirming that this radiation originated from thermal equilibrium in the early universe. The surface of last scattering where these photons originated lies at a current distance of 46 billion light-years, forming an impenetrable barrier in our past. No electromagnetic radiation from before recombination can reach us because the early universe was opaque to light. Recent observations by the New Horizons spacecraft measured the cosmic optical background, the accumulated visible light from all galaxies, at approximately 15 nanowatts per square meter per steradian. This measurement suggests the cosmic optical background is roughly twice as bright as expected from known galaxy counts, with the remainder potentially indicating undiscovered faint galaxies or systematic uncertainties in our galaxy counts. What began as Heinrich Olber's staring at a dark sky in 1823 ultimately revealed that our universe had a beginning, carries the signature of its birth in every cubic centimeter of space, and will have an end. The resolution required discovering that space has an age, that the cosmos expands, and that light itself can be stretched beyond human perception by the fabric of space-time. Every dark patch in the night sky represents a region where insufficient time has passed for light to reach us, marking the universe's youth at just 13.8 billion years old. The missing brightness that should make the sky blaze surrounds us constantly as microwave radiation at 2.7 degrees Kelvin, the afterglow of creation itself. Modern space observatories continue refining our understanding, with missions like Planck providing the most precise measurements of this cosmic background light. The darkness above us tells the story of cosmic time, revealing that we live in a universe still young enough for night to exist, still cool enough for stars to shine against the black, and still expanding fast enough to hide its own brilliant past in wavelengths our eyes cannot see. In 1965, Penzias and Wilson thought they detected equipment noise. Instead, they found the echo of the Big Bang itself, solving a puzzle that had stumped scientists for centuries, and proving that sometimes the most deep answers hide in plain sight, waiting for the right instruments to reveal them.